In 11.2b and c, we're going to use the Chisquare test of homogeneity to determine whether a distribution's categorical variables differ from several populations or treatments, and then we will examine individual components of that chi-square statistic for follow-up analysis. Before we start that, though, I want us to go back to this example where it's almost related to more Chapter 1. So just follow along. An article in the Journal of American Medical Association reports that results of a study designed to see if the herb St. John's wort is effective in treating moderate to severe causes of depression. The study involved 338 subjects who were being treated for major depression. The subjects were randomly assigned to receive one of three treatments: St. John's wort, an herb, Zoloft, a prescription, or a placebo for an 8-week period. The table summarizes the results of the experiment. So here are the three different types of treatments, and here is the type of responses that they recorded. So either a full response, a partial, or no response. And again, our total of 338 individuals. So here is a conditional distribution of the types of responses for each treatment on the graph. So you have to remember, how do you condition on treatment? So the treatment for this case would be looking at St. John's wort, for just looking at Zoloft, and the placebo. So remember, for the conditional, what they did is they took 27 divided by 113, 16 divided by 113, 70 divided by 113. And they just wrote their answers here more in a row versus in the column we see above. Keeping in mind, all three of these values add back to 100% because they conditioned on treatment. They then took each of the three treatments and they color-coded if it was a full, partial, or no response, and you see a nice stacked bar graph. What they want us to do on the next slide is compare the distributions of response for each treatment. So let's take a look at these and make some conclusions about what we see. One thing you could say is this: the higher proportion of subjects receiving the placebo had a full response compared to subjects receiving St. John's wort or Zoloft. Another comparison you might make is this: that the higher proportion of Zoloft users had at least some response, followed by placebo users and then St. John wort users. This here is a good review of just what Chapter 1 and how it works, but it's also a nice segue in talking about our next Chisquare test. So ultimately, there's going to be 3 Chisquare tests. We remember from 11.1 our goodness of fit test. When did we use that? We used the goodness of fit test to test the distribution of one categorical variable from a sample of one population. So remember, we looked at, for our main example, the color, so that was one category, for one bag of M&Ms. So 1-to-1 kind of thing. In 11.2, the first test we're going to look at is called the Chisquare test for homogeneity. How you tell if you're going to do that one is this: you actually test the distribution of one categorical variable, so for example color, from a sample of 2 or more populations. So in this case, we would still look at if it was color for our M&Ms, but we have to have 2 or more populations. So maybe we're looking at M&Ms and Skittles, and we're comparing if there's a difference between those. And then the last one we'll get to is the Chisquare test for either independence or association. You can use either word for that. And what that one is a test of independence of 2 categorical variables from one sample or population. So in this case, how does it differ? Maybe we're looking at 2 categories of that one population of M&Ms. Maybe we're looking at color, and maybe we're looking at weight to see if there's an association between those 2 elements. If this slide makes sense to you right now, this is really all you need to know in picking which one of the 3 Chisquare tests that we'll do, but we will spend some more time on practicing that. If you recall from the goodness of fit, there are multiple comparisons for a Chisquare. There's really 2 parts to it. The first part is test to see if there's good evidence of any differences. And then if you are asked for it by the AP board, you will do a follow-up analysis to determine which parameters differ and estimate how large the differences are. Now, when we do the Chisquare test of homogeneity and the association and independence, it's slightly different than the goodness of fit. I would say the goodness of fit test is a little bit easier. This one here in 11.2 is just a little twist to it, and it's about the expected counts. For these, you have to find the actual expected counts from a 2-way table and not a 1-way table. So to do that, you're going to have multiple rows and columns, And all you have to do is this. The expected counts are going to be the total of the row times the total of the column over the total in the table. So for example, let's say you had a two-way table where this row totaled 20 and this column totaled 50, and you wanted to find the expected counts for the element in this cell. Well, the table in total is going to come back to 300. So what you would do to find the expected count for this particular cell is look at the row total, which is 20, the column total, which is 50. So you do 20 times 50, and then you're going to take that and divide it by the total of the table, which is 300. That will give you the expected counts for that particular cell. This formula here for expected counts is not on the AP formula sheet, so you do need to make sure you know this. There's no way you're not going to be asked this question on at least a multiple choice question at a minimum, so know how to compute expected counts for a two-way table. Let's just look at the St. John's wort example again. Notice again, it's a two-way table because we have your treatment and we have the responses here. There's two different things. What I can do to figure out the expected counts, we know the observed count for St. John's wort at a full response is 27. But the expected count would be, look at the row of 91, look at the column of 113. The table total was 338. So notice what I'm going to do here. I'm just going to show for the St. John's wort full response is going to be 91 times 113 on the top, and you divide it by 338. We would expect there to be 30.4 responses compared to our observation. And then you would just do that for all 9 of these cells to get all the expected counts. Now I will tell you the conditions are going to have to be met, like before, that all the expected counts are still 5. So to do this one is actually a little bit of work. Let's just change it for Zoloft, right? For Zoloft, it's going to be 91 and 109. It's going to change. But you have to show these totals somewhere. You don't necessarily have to show the calculations to get there, but you have to show all 9 expected counts and that they are greater than 5. Again, don't fall into the thing of rounding your expected counts. At least go out to 1 decimal place at a minimum. Because an expected count is theoretical. It's not what we would actually expect to truly happen. Now, if we continue on this, I will tell you the chi-square distribution calculation is exactly the same. It's observed minus expected squared over expected, and you add them up. So if you do that, what you're going to end up getting is the chi-square statistic for this is 8.72. However, it's very unlikely that you're actually going to compute this one by hand. They might ask you to do goodness of fit, but probably not for the test of homogeneity. Let me show you how to do the calculator for this one because it is more involved. The screens we're going to use on the calculator are dealt with the matrices, and the other output you want to look at is this. So ultimately what you're going to do is you're going to go to your stat and your tests, and we're not going to choose the GOF test for chi-squared. We're going to choose the other one. It's just the chi-squared test. When you choose that, you're going to notice it says, oh, what is this? It is looking for your observed and your expected values. Actually, the only one you manually have to type in are your observations. When you run the test, it will actually populate the expected counts for you in matrix B. So where do you put this data? To get it in here, you actually have to find where matrices are stored. And the matrices are stored at a second level. So you're going to notice the math button. Right below the math button is x to the negative 1 power. And above that it says the word matrix. That's what you need to find. So hit second, that x to the negative 1 power, and you will get to the names screen. Well, just like in stat edit for the lists, you actually have to go to the edit to put information in. So scroll over to edit while you're on matrix A and hit enter. All you have to do is if you need to change the dimensions of your matrix, in ours it's rows by columns. So we have 3 rows and 3 columns. So I would type 3 by 3. And then you literally just type in the observed values that you're seeing right here. Now, you do not have to go and type in B. Again, those will get calculated once you do the test. So once matrix A is populated, go back to your stat tests and run the chi-square test. Observed is done, expected will get created. Go to calculate. When you do, you're going to get this information right here. Notice that the chi-square statistic is exactly what we said it would be. The p-value on here is about 6.85%, and the degrees of freedom on here is calculated differently for this test. Do make note of this. The degrees of freedom for the test of homogeneity is going to be the number of rows minus 1, and you times that by the number of columns minus 1. So if you look at this one here, we have 3 rows and 3 columns. So you would end up doing a 3 minus 1 or 2 times a 3 minus 1 or 2. So your degrees of freedom is going to be 4, and that's why the calculator comes up with the 4 for degrees of freedom. So the manual degrees of freedom that you would compute will actually be the same as the calculator. Now, you can conclude the test right here, but you have to be cautious, and we will do one from start to finish. In your plan section, remember, all expected counts must be at least 5 or higher. If you do not want to calculate them manually, your calculator will have it. Look back at this test screen. Folks, this says the expecteds are going to be stored in matrix B. How do you go to that? You're going to go back to second x to the negative 1 or matrix button. If you scroll down to B and scroll over to edit, you can hit enter and you can actually see all the expected counts computed for you. Do notice when you're in this test mode here, you also can go down to draw if you want to get a nice picture of the probability and the chi-square. So the chi-square statistic and probability will be seen here in this image. Now, one thing to make note about the chi-square test for homogeneity. Remember that this test is all about analyzing one category, such as color, and 2 or more populations. Well, this test sometimes can be done a different way. The homogeneity just means the same or composed of like parts. So it's used when we have 2 or more groups, and we want to know if the category proportions are the same for each group. Well, you guys, in Chapter 10, we just got doing comparing proportions from 2 groups. We did the 2 sample z-test for difference of proportions. So there will be times if you read a problem and it reads like one category and it's exactly 2 for the population, you will have a choice. You could actually do the chi-square test for homogeneity, or you could do the 2 sample z-test for difference in proportions. The AP board is not going to care which one you do as long as it's done adequately and the conclusion is made properly. So let's talk about the key things to think about for chi-square tests of homogeneity, which is our second type of chi-square test. So suppose the conditions are met, how do you state the actual hypothesis? For this type of test, what you would say is there is no difference in the distribution of the categorical variable for several populations or treatments, depending on exactly what you're looking at. So therefore, H sub A, you would just say there is a difference in the distribution of a categorical variable for several populations or treatments. It's basically just the complement of the H sub O. To get started, the first thing you're going to do is actually find your expected counts. If you have those, then you can actually calculate the chi-square statistic using the formula from before, observed minus expected squared over expected, and you add it up for every single cell or observation. Now, when you find the p-value using your chi-square statistic, remember you have to find your degrees of freedom. For this test, your degrees of freedom is going to be your number of rows minus 1 times your number of columns minus 1. And then for the graph, the p-value is the area to the right of the statistic underneath the chi-square density curve. The conditions are the same as they were for the goodness of fit. The first thing you're going to want to do is check for randomness, that the separate random samples, or you have groups in a randomized experiment. The large sample size, all expected counts must be at least 5. And for independence, both samples or groups are independent. Or, if you are sampling without replacement, you must check the 10% condition for all your populations. Again, the AP board is going to remind you, don't make the common mistake in your condition checking. You are actually checking the expected counts, not the observed counts, for the large sample size condition. And you must list the expected counts as part of your checking of the conditions. You just can't say that they are greater than 5. You have to write them all out. Things to keep in mind for the chi-square test of homogeneity. The first one is that the expected counts and the degrees of freedom are calculated differently than they were in the goodness of fit test. So make sure you keep them straight between homogeneity and goodness of fit. The expected counts, recall, you're going to take the total row times the total column over the table total. For degrees of freedom, that's number of rows minus 1 and number of columns minus 1. Again, I'm going to encourage you to reference the handout sheet I gave you at the beginning of Chapter 8. For the calculator, the test for homogeneity and chi-square test of independence can be performed on your calculator. The observed counts must be entered into the matrix for matrix A. Remember, after you run the test, the expected counts will actually appear in matrix B. So you could actually piggyback off of what goes into matrix B if you don't actually want to compute the expected counts by hand for every single cell. Now let's refer back to the two-way table we had about using St. John's wort, Zoloft, or a placebo to help minimize depression. Earlier, we could have said that the hypothesis for that was H sub O, there's no difference in the distribution of responses for patients with moderately severe cases of depression when taking St. John's wort, Zoloft, or placebo. However, H sub A, we think there is a difference in the distribution. So the only difference here is using the word no for H sub O as we don't in H sub A. Now they computed their chi-square statistic and got an 8.72. Let's first verify the conditions for the test have been satisfied. So this is an experiment, and in this case, the treatments were randomly assigned, so we're fine. I do recommend, as you would actually run the test on here and then go look at your expected counts in matrix B. If you write them all down, you're going to see that these were all of the expected counts. You need to list them out and say that they are at least 5. Now be careful, this says at least 5, including that would be 5 or greater. And then for independence, knowing the response of one subject should not provide any additional information about the response of any other patient. So in this case, because it is an experiment, you would not do the 10% condition. You just need to realize that it was set up appropriately so there is independence within this actual experiment that's being conducted. Now, do know that I have read many free responses from the AP board and their answer keys. One time I have seen in the correcting rubric, all you would state is something like this for independence. It actually stated on there, if the student computes the 10% condition to check, you would actually lose some points. I've only seen it one time stated that way. Other than that, I don't know if they would technically dock you if you check the 10% condition, even though you don't need it, because this is an experiment. Remember, the 10% condition is only if you are sampling without replacement, and there is no independence in the situation as it stands. To calculate the p-value for this, we have the chi-square statistic. We do need the degrees of freedom. Degrees of freedom is rows minus 1 and columns minus 1. So that's going to give us 4. The p-value for this, remember on chi-square how it works, it is the statistic that we have all the way to the right. So make sure you keep that straight. The p-value therefore is going to be our 8.72 to a very large number, 4 degrees of freedom. Our p-value is 6.85%. A good review question is interpret the p-value in context. So let's recall that. The p-value is this. Assuming that the treatments are equally effective, the probability of observing a difference in the distribution of responses among the 3 treatment groups is large or larger than the one in the study is about 0.07. So really remember what this says. The beginning part says, assume that the null hypothesis is true. That's what this first component is saying. Assume the null hypothesis is true. This is really the probability of getting our treatment group or larger, which is actually important to say, in that it would be a probability of, again, rounded to 0.07. Okay, let's do our conclusion. In this, the p-value is greater than alpha, so 0.07 is greater than 0.05. Therefore, we are going to fail to reject the null hypothesis. Now be careful in the conclusion. The easiest way to say this, We do not have convincing evidence that there is a difference in the distribution of responses for patients with moderately severe cases of depression when taking St. John's wort, Zoloft, or a placebo. The easiest way to do this is just to take H of A and say, we do not, and you should be just fine. However, keep in mind, if we had rejected H sub O, we would just conclude H sub A as it's stated in context. Let's wrap up these notes with revisiting the question about superpowers that we saw way back in Chapter 1. Back then, they actually asked 200 students in their sample who were from the United Kingdom in ages of 9 to 17, which superpower would you want to have? Well, we're going to go beyond that one because the UK is our first sample. We're going to make this not a test of goodness of fit, because goodness of fit would just be looking at your superpower in the UK. We're going to have this go beyond to become the test of homogeneity by adding a second sample. So in here, our second sample is the US. So they surveyed 215 students and asked them the same thing, and these are their results. So let's first start by constructing an appropriate graph to compare the distribution of superpower for the UK versus the US students. Now, a side-by-side bar graph might be nice for this. And what we would do is, because the counts are different, you must be careful. You cannot do frequency in terms of your bars. You must do relative frequency or percents. So you have to compute and compare your 54 over 200, your 52 over 20, and compute the percent of the students. That is, we condition on the actual superpower. If you do this, you would get a graph that might look something like this, where we have, again, conditioned by superpower for preference. That is, if I were to add up the UK, which is all of the blue bars, we would see 100% of the student responses, and the same with the US. And notice they did the proportion again and not the counts, because they're not equally sized groups. Part B wants to know, do these data provide convincing evidence that the distribution of superpower preferences differs among the US and the UK children? That's a good question. So let's just do state, plan, do, and conclude. In this case, we do want to perform, it'll be a chi-square test of homogeneity, because we are looking at one category but two or more samples. In this case, two exactly. So I'm going to state that we want to perform a test for the following hypothesis. We're going to use an alpha of 5%. I'm going to start with the null hypothesis. There's no difference in the distribution of superpower between the US and the UK students. But I do think there is, so H sub A, there is a difference in that distribution of superpower. My plan, again, let's just check for the randomness on here. So the data are from separate random samples of the UK and the US children, so we have that. We do want to check the large sample size and the independence. So for the large sample size, you can either compute your own expected counts. Remember to do that if we wanted to do it, for example, for the UK kids at fly time, I would just do row times column over the total of 415. So for this, it would be 99 times 200 over 415 would give me this expected count. Or I can actually put my observed values in matrix A, run the chi-square test, and then go back to matrix B and just jot these values down. Double check that they are at least greater than 5, so we're good with a large sample size. For the independence component, the samples were independently selected. Also, since there are more than 2,000 children in the UK and more than 2,150 in the US, both samples meet the 10% condition. And then I don't have it written down here, but let's actually write the test we're doing. I do know the name, so I'm going to say it's a chi-squared test for homogeneity. Now the AP board will give you some advice about naming the test. If you can't remember specifically if it's for homogeneity or goodness of fit, they would recommend that what you write down as a minimum is just say it's a chi-squared test and just leave it at that. They would almost recommend not to guess unless you're pretty certain it's homogeneity. Because if you are doing, for example, the goodness of fit test and you say homogeneity, you will lose a point. However, if you just put the chi-squared test, they may actually give that to you because it's somewhat of a broad answer. But I will say, if you do know it's homogeneity, please do write that down. So for this one, I obviously am going to use the calculator, and I'm going to put my observed counts in the matrix and run the chi-squared test under my test. If I do that, I can get the chi-squared statistic, so I would jot that down where it's 6.29. The p-value, we are going to be using the degrees of freedom, is the rows minus 1 and columns minus 1. So in this case, our degrees of freedom is 4. If we were to calculate the p-value by hand, it'd be the chi-squared CDF of our 6.29 to a really high number with, I should put in here, be careful, 4 degrees of freedom. And when you do that, you're going to get a p-value of 0.1784. Now let's go ahead and make our conclusion for this. Our p-value is greater than alpha, and I'm just going to write that down to double check that, show the AP board I've compared it. Because of that, I'm going to fail to reject H sub O, and remember my conclusion would be that we do not have convincing evidence that there is a difference in the distribution of superpower preference for the US and the UK school children. You're asked to do a follow-up analysis on the test of homogeneity. What you're going to do is you're going to come on in and you will start by finding the cells with large deviations between observed and expected. So you can look at matrix A and look at matrix B and see where the larger deviations are. You can also look at the individual components to see which contribution most to the chi-square statistic for that. When do you actually do that follow-up analysis? Remember, you only do it when you're specified to do so. I have yet to actually see the AP board ask you to do a follow-up analysis on a test of homogeneity. However, I have seen multiple choice questions where they will show you the chi-square distribution and how it is deviated between each of the cells. So you'll see how the statistic was actually built. And then from there you could easily do an analysis and find the chi-squares that deviate the most from each other. Remember, that could be in terms of the amount, or if you have a lot of positives and only a few negatives, maybe you look at the ones that are sticking out because they're outside of the pattern and are negative.